intermolecular forces, and in this video we're looking at polar molecules. My intermolecular forces could be dipole to temporary dipole, they could be dipole-dipole, they could be hydrogen bonding. Some molecules are permanently polarized because of a difference in electronegativities of atoms forming the bond. A dipole-induced dipole attraction is a weak attraction that results when a polar molecule induces a dipole in an atom or in a non-polar molecule by disturbing the arrangement of electrons in the non-polar species. Hydrogen chloride, HCl, has a permanent dipole. Hydrogen has an electronegativity of 2.2 and chlorine an electronegativity of 3.2, and that difference causes the polarization. Hydrogen shown as having a partial positive charge, chlorine as a partial negative charge. Now, if that polar molecule lines up with a non-polar oxygen molecule, electrons in the double bond of the oxygen can be repelled away by the slight negative charge on the chlorine part of HCl, creating a temporary dipole. The higher electron density around Cl repels electrons in the oxygen molecule, causing polarization and attraction between the two molecules. Since the polarity of HCl is permanent, the attraction is stronger than London dispersion forces. Permanent dipole to permanent dipole forces of attraction are much stronger than London forces. They exist when molecules attracted to each other are permanently polar. I take my hydrogen chloride again, H as shown as having a delta plus slightly positive charge, Cl slightly negative. The delta plus on the hydrogen atom of one molecule is attracted to the delta minus on the chlorine atom of another molecule. This makes the molecules more difficult to separate than they would be without the intermolecular force, and so it raises the boiling point. Molecular polarity depends on molecular geometry as well as bond polarity. Bonds are polar if there's a significant difference in the electronegativities of the elements forming the bond. However, we can have polar bonds and not have a polar molecule. In CCl4, all of the bonds are polar, but there is no positive end of the molecule. If I look at my first diagram on the left, each carbon to chlorine bond is polar, but the central carbon with the delta plus is surrounded by negative charge on the 4 chlorine atoms. The carbon atom does have a slightly positive charge, but it's surrounded by chlorine atoms. If we consider the pull of the chlorine atoms for the electrons to be a vector, there's no net vector. Molecules that have a center of symmetry are never polar, whether they have polar bonds or not, because there is no positive end to the molecule. There is no net dipole moment. If one of the chlorine atoms were replaced by another atom, then the molecule would be polar. And we see that with CH3Cl, a polar molecule. CH3Cl is a polar molecule, no center of symmetry. The molecule has positive and negative ends. CCl4 has a center of symmetry, the molecule is nonpolar. We have dipole attractions in CHCl3, but not in CCl4. We must remember that London dispersion forces and dipole-dipole forces are examples of van der Waals forces. Whenever we have London dispersion forces, or dipole-dipole forces, we also have van der Waals forces. Hydrogen bonding occurs when hydrogen is bonded directly to a very electronegative element. Those elements are fluorine, oxygen, or nitrogen. Only those three elements. Since fluorine only makes one bond, as fluorine is in group 17, we really only focus on compounds containing OH and NH bonds. With fluorine in group 17, only makes one covalent bond. Once it's bonded to hydrogen, in hydrogen fluoride, it cannot bond to anything else. And so there's only one molecule, HF, only one molecule involving fluorine that makes hydrogen bonds. Very different with oxygen. Oxygen in the diagram I see bonded to two hydrogens. That will give hydrogen bonding. The second of those bonds could be to anything else including carbon, and that means there's an immense number of compounds involving oxygen that could form hydrogen bonds. Why is it so important? Hydrogen only has one electron, and if this is pulled away from it, there's nothing but a proton at the other end of the bond. This makes hydrogen bonding the most powerful form of dipole-dipole bonding. It's the strongest of all the intermolecular forces of attraction and can be 10% of the value of a covalent bond. Two compounds given at the top of the slide. The compounds should have very similar boiling points. They both have formula C2H6O. But the first compound boils at negative 24 degrees, whilst the second one, which is ethanol, boils at plus 78. The reason for the large difference is that we have hydrogen bonding in the second molecule, as the hydrogen is bonded directly to oxygen. Polar hydrogen bonds not only raise the boiling point, they also make a covalent compound more soluble in water, as water is a polar solvent and hydrogen bonds can form between the two. Here I see the second structure given above, which is ethanol, with its polarity shown between the oxygen and the hydrogen, forming hydrogen bonds with a water molecule as it goes into solution. Finally, three compounds: ethanol, ethanal, propane. Their boiling points given: ethanol at 78 degrees, ethanal boiling point about 20, propane about negative 42. Ethanol can also be compared to propane, as we have, and ethanal, as they have very similar molecular mass. Now, propane is non-polar and boils at negative 42 degrees because the only intermolecular forces are London dispersion forces, the weakest form of intermolecular forces. Ethanal has a permanent dipole between the carbon and the oxygen. You could say van der Waals also, and boils at a much higher temperature of 20 degrees. This is a lot less than the 78 degrees that ethanol boils at because ethanol has hydrogen bonding. If intermolecular forces are stronger, then the particles are harder to separate. Since boiling involves separating particles into the gas phase, stronger intermolecular forces means a higher boiling point. That's it. Hoping you found that useful. If you did, please hit like. Please subscribe to be informed of more content.